I'm going to go through how to answer questions related to trends of the periodic table for the higher chemistry course set by the SQA. So, to tackle these questions, you need to be aware of two concepts. The first is what's called nuclear charge. Okay, and that's essentially the attraction that the positive protons have for the negative electrons. In the atom. Okay, and because it's about an attraction, the more protons you have, then the stronger the nuclear charges. Okay, and that applies for across a period and going down a group. The second thing you need to be aware of is something that we call the shielding effect. So with some sources, depending on where you're looking, you might also see this called the screening effect. So the shielding effect, which is how well the electrons are protected from that nuclear charge. And it's to do with energy levels, or electron shells. Energy levels we'll stick with. So essentially, the more occupied energy levels you have, the greater the shielding effect. So your electrons, which I'm going to abbreviate to E minus, so your electrons are less strongly let's just say less attracted to the nucleus. Okay, hopefully as we go through the three main areas where these two things apply, it will start to make a bit more sense. But nuclear charge is to do with protons, and the more protons you have, the stronger the nuclear charge. And the shielding effect is to do with energy levels. The more energy levels you have, the larger the shielding effect, or the more effective the shielding is. Okay? Okay, so the first trend we're going to look at is the covalent radius, or the atomic size. Alright? In general, as you move down a group, your atomic size increases. And across a period, we have a decrease. Okay, and we're going to explain why. So, let's start with going down a group. If we look at group 1, we don't include hydrogen in group 1, so we're starting with lithium. What we have, lithium has an atomic number of 3, which means it's got 3 protons and 3 electrons. Okay, and this information here tells me the number of electrons in each energy level. So the 2 tells me I've got 2 electrons in the first energy level and 1 electron in the second. Okay, moving down the group to sodium, it's got an atomic number of 11 protons and 11 electrons, 2 in the first one, eight, please forgive my drawings, 3, 4, 5, 6, 7, 8. Okay, 8 in the second one, and then in the third one, with my terrible drawings, we've got just 1. Okay, now, the reason I drew them is to give you a clearer picture of this shielding effect. So, we have gone from lithium for a atomic number of 3, which means I've got 3 protons, so a nuclear charge of 3. Okay, with sodium, it's an atomic number of 11, so 11 protons, I've got a nuclear charge of 11. So as I go down the group, the nuclear charge increases because the number of protons also increases. However, the number of occupied energy levels also increases. With lithium, I have a total of 2 energy levels. Sodium, I've got 3. 1, 2, 3. If I was to draw potassium, I would have 4 energy levels. Okay, so these energy levels are your shields, if you like. The more energy levels you have, the greater shielding you have for the electrons from that positive charge. Okay, so as you move down a group, the shielding effect increases, which means that the electrons are not as strongly attracted to the nuclear charge. They don't feel the nuclear charge as much. Okay, as you move across a period, however, if I look at, let's do carbon, nitrogen, and I'm going to do these ones green. So if I draw, let's do boron to start with. So I'm going across this time. We've got 1, 2, 3, 4, 3, 4, 5. Moving along one, I've got carbon. So I've got 1, 2, 3, 4, 5, 6, and I'll just do nitrogen. Got 1, 2, down a group, you have more occupied energy levels, so a greater shielding effect. Electrons are not as attracted to the nucleus. They are actually also physically further away from the nucleus. Okay, so that is atomic size. The next trend that we're going to look at is electronegativity. So electronegativity increases across a period and decreases as you move down a group. The electronegativity values of the elements can be found on page 11 of your data booklet. Okay, so what is electronegativity? Electronegativity is the measure of attraction an atom has for its bonding electrons. Okay. The higher the electronegativity value, the higher the electronegativity, if you like. So the bigger the number, the higher the electronegativity. So it's a measure of attraction an atom has for its bonding electrons. Now, it increases as you move across a period, and that is because, so I'll do across the period in green, keep it consistent. So across the period, the nuclear charge or the number of protons is increasing okay, and this means that the atom is better at attracting other electrons. Okay, as you move down a group, Okay, so as you move down the group, you've got more occupied energy levels. So the Okay, so as we go down the group, you've got more occupied energy levels, so the nuclear charge is less effective at attracting other electrons. Okay. Okay, the next one we're going to look at is ionization energy. So again, you're really thinking about the nuclear charge and the effect of shielding, but with this trend, you can also be asked about ionization energies of different elements and the removal of more than one electron. So I'm going to explain what that means. So the first thing you need to know is what is ionization energy, and it's defined as the energy required to remove 1 mole of electrons from a gaseous atom. Now I'm going to explain what that means. There's two things you need to be aware of. The first one is gaseous, and the second one is 1 mole of electrons. With the 1 mole of electrons, read it as energy required to remove 1 electron from a gaseous atom. Okay, now if we look at lithium as an example, you start with an atom. We can do ion electron equations to represent ionization energy. So let's look at lithium as an example. We have lithium as an atom. It has to be in gaseous form, so I'm going to use the state symbol G. I'm removing 1 electron, so that is going to then give me lithium, a lithium ion in a gaseous form plus an electron. Okay, now that equation represents what would be called the first ionization energy. Okay, but it is actually possible to go on and do second and third ionization energies as well. So if you were asked in a question to show the ion electron equation for the second ionization energy, then instead of starting with an atom, as you did with the first, you would start with an ion that has a 1 plus charge. So lithium plus. It still needs to be in the gaseous form. We're removing another electron, so now it becomes 2 plus, and then plus E minus. And that would represent the second ionization energy. Okay, now need to put the gas there. This is one of the only examples, or the very few examples, where the SQA would require you to include the state symbol to gain the mark. Okay? What we're now going to do is apply the idea of ionization energy, the removal of an electron, to the periodic table trends. So, leaving the definition up as a reminder, we're now going to apply it down a group and across the period. So, let's go across first of all. As you move across the period, this idea of nuclear charge increases. The number of protons increases, so the nuclear charge also increases. If ionization energy is the energy I need to put in to take an electron away, then the stronger the nuclear charge is, the more energy is required to remove an electron. So, as you move across a period, your ionization energy increases. And to put that into words, across ionization energy, which I'm just shortening to IE, increases as nuclear charge increases. Meaning the electrons are more tightly held. Okay, so the stronger the nuclear charge, the more able it is, the atom is, to keep hold of its electrons. As you go down a group, you're adding an energy level. That energy level increases shielding. So down a group, there are more energy levels. So greater shielding. Electrons are not as attracted to the nucleus, so easier to remove. Okay. So we have a decrease. The other thing that you could be asked about when you're looking at ionisation energies is to compare the energies between a first ionisation energy and a second ionisation energy. So I'm going to go back to lithium to explain why that is. Actually, I'll use sodium. So if we look at sodium, it has the electron arrangement 281. One, two. Okay. First ionisation energy would look like this. So Na gas becoming Na positive plus an electron. Now, that plus an electron comes from here. You are removing that electron. And when you do that, you actually, so this is the first ionisation energy. When you remove that electron, you actually remove the energy level as a whole, because it only had one electron anyway. Okay? That leaves you with what we'd call a stable octet. The remaining energy level has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. When elements reach an octet, they are stable. They do not want to react any further. Okay? Now, the first ionisation energy for sodium is given as 496 kilojoules per mole. Okay. The second ionisation energy would be Na positive becomes Na2 plus E minus, and that would be your second. Okay, now the energy associated with that jumps up to 4,562 kilojoules per mole. It's a massive jump, and the reason it's a massive jump is because you would be removing one of these electrons and upsetting the stable octet. Okay, the atom or the element would want to resist that as much as possible, and so that's why it takes so much energy to take that second electron away. Alright, it's also less shielded from the nuclear charge. It's more strongly attracted to the nuclear charge, and so it's going to take more energy to remove. Okay, we're now going to apply what we've covered to some past exam questions. These questions have come from the 2016 higher chemistry paper. Okay, what you have here is a graph of elements showing the covalent radius and the ionic radius, and this question is worth 1 mark Explain why covalent radius decreases from across the period from sodium to chlorine. Okay, so why does the atomic size decrease, or the covalent radius decrease, from sodium to chlorine? In terms of answering, it's a 1 mark question. So it decreases because the nuclear charge is increasing. And this pulls the electrons in closer. Okay, now in terms of marking, the SQA would accept just the nuclear charge is increasing. They would also accept, in place of nuclear charge, they would also accept number of protons is increasing. Okay? This question, part 2 of the question that we've just looked at, is a 2 mark question, and so a bit more information is required. So we're asked to explain fully why the covalent radius of sodium is larger than the ionic radius of sodium. So we already know that covalent radius represents the size of an atom, and then we're asked to compare it to the ionic radius and explain why it's larger. Okay, so 2 marks. So there are 2 distinct points that we need to cover here. The first thing I would do is show that you have an understanding of the size of a sodium atom compared to the size of a sodium ion. So what do I mean by that? If we look at sodium atom, just move that across. Again, forgive my wonky drawings. Okay, so that's the sodium atom. That is the covalent, or represents the covalent, the structure for the covalent radius, if you like. Okay, when we form an ion, then this electron will disappear. So it becomes this. And you'll have a positive charge there as well. Okay, we've gone from 11 electrons here to 10 here for the ionic radius. Okay, drawing those 2 structures would be one mark. Okay, you could also explain it using words. So something along the lines of the covalent radius of sodium represents the atom with 3 occupied energy levels. The ionic radius represents the ion which occupies 2 energy levels. Okay, just something along the lines of showing that you understand that one has 3 occupied energy levels and the other has 2. Your second mark is for then linking it back to your trends. So since the sodium atom has shielding, the electrons are less further away and less attracted to the nucleus. Okay, so that would then be your second mark. It's worth saying that I focused on the sodium atom for the second part of my answer, but you could also write that the sodium ion has less energy levels and so less shielding, and the electrons are closer to the nucleus and more attracted. Either of those would get you the answer. There's no preference. This question is similar to the two that we've done previously. You might want to pause the video and have a go before we go through the answer together. So, this question, similar graph, you've got elements, and this time we're looking at ionisation energy. You've got the first ionisation energy and then the second ionisation energy. So, the first part of the question is explain why the first ionisation energy decreases going down group 1. It's worth 1 mark. So, going down group 1, ionisation energy decreases, and that is because of the addition of energy levels. So, more energy levels means electrons Okay, so more energy levels means electrons are shielded from the nuclear charge, easier to remove electron. The more shielding there is, the less attraction the electrons have for the nuclear charge, the easier it is to remove the electrons. Okay, the second part of this question, again, is similar to the one that we've done before. It's 2 marks, so we're looking for 2 points, you might want to pause, have a go at it, and then have a look at the video to see how well you've done. So, explain fully why the second ionisation energy is much greater than the first ionisation energy for group 1 elements. Okay, now, just for clarity, if we look at lithium as an example, okay, lithium has the atomic number 3. 3 electrons. 1, 2, 3. Okay, now in terms of first ionisation energy, it's this electron that's going to be taken away. So in terms of ionisation energy and first ionisation energy, it's this electron that's going to be taken away first. And I am abbreviating ionisation energy to 1, so IE, sorry. Your second ionisation energy is going to then have to come from the innermost energy level. Okay, so what do you need to write? 2 points. The first one is a point about stability. So removing a second electron means removing it from a stable or full energy level. And remember that the first energy level of any element can only hold 2 electrons. So in lithium's case, the fact that once you've removed the first electron, you're left with 2, that is actually stable. Okay, that would get you 1 mark. Your second then is for linking it to shielding and nuclear charge. So remaining electrons are closer to the nucleus slash more affected by the nuclear charge. More energy is required to remove the electron. Okay, and that would then be your second mark. So your first mark is for mentioning that removing a second electron upsets your stability, And your second mark then is for linking it back to this idea of nuclear charge or shielding. Okay? The final questions we're going to have a look at are multiple choice. Again, you may want to pause the video, have a go at them before looking at the answers. So, all of these questions are relating to trends in the periodic table, and we're going to start with the one in the top left hand corner, which is which of the following equations represents the first ionization energy of chlorine. So the first thing you want to do is have a look for any answer that does not start with an atom. So if we have a look at B, we see that it's got a positive charge. That means that it's already an ion, and so you would actually, that would be the second ionization energy. Okay, D also has a charge. It's worth pointing out as well that in this case all of the elements are in a gaseous state. Sometimes that isn't the case, and if you see an equation where it starts with anything other than a gas, you can immediately discount it, okay, if it's asking about ionization energy. You're now then left with A and C, okay? Remember that ionization energy is the energy required to remove an electron, or 1 mole of electrons. So you want to then end up with a positive ion because we're going to lose an electron. Given that, your answer would be C. Okay? A couldn't be your answer because the ion that is formed has a negative charge, which means it's gained an electron. Okay? It would almost be the reverse of ionization energy. So we're now going to look at this question here, and you may have noticed that I've already jotted down some numbers. These numbers here are the electronegativity values for the elements. You will find them on page 11 of the data booklet. The question is, which of the following atoms has the least attraction for bonding electrons? Okay, that is another way of saying which of these elements has the lowest electronegativity. Okay, the higher your electronegativity, the higher the attraction for bonding electrons. So you would go to page 11 of your data booklet. You would have a look at your electronegativity values. So carbon is 2.5, nitrogen is 3, phosphorus is 2.2, and silicon is 1.9. Okay, and from there you're just selecting the element with the lowest value, which is D. Which entry in the table shows the trends in electronegativity values of the elements of the periodic table? So across the period, electronegativity increases, which means that we can get rid of automatically A and B. Okay, and they increase because of an increase in nuclear charge. And down a group, electronegativity decreases because of shielding. So your answer is C. A potassium atom is larger than a sodium atom because potassium has what? So we're going down group 1 here, sodium down to potassium. When you move down a group, you add an energy level. So your answer is C, more occupied energy levels. The difference between the covalent radius of sodium and silicon is mainly due to the difference in the something. Okay, so covalent radius is another way of saying atomic size, and we're moving across a period. So we're looking for the number of protons because that is representative of the nuclear charge. So I hope you found this tutorial helpful. In the description of the video I will put some information of where you can find additional questions to help you along the way, and there will be more videos to follow.